Let's look at a very important result from integral calculus. It's basically the differentiation theorem. And there are two parts to the fundamental theorem of calculus. There is the differentiation theorem, and there is the process of computing a definite integral. So I like to do this in two parts. And you'll find this proof in your notes, but I think it's important that we have a video to go over it. So what we're going to do is suppose f is continuous on a closed bounded set AB, and we make a definition, a function of x, that is g of x is the integral from a to x of f of t dt. And we use different letters here just so you don't get confused with x, even though a lot of times we don't worry about it. And then of course x will be in the closed bounded set AB. Then the derivative of the g, that is the x derivative of the integral function, is actually f of x. So basically, when we think about our definition of antiderivatives, the g is an antiderivative of f. That's basically the definition. And so this tends to promote the idea that the differentiation and integration processes are inverses of each other. So that's one way to remember it. So how do we prove this? Well, I'm going to use the alternate definition of derivative. So it's going to suffice to show that g prime of c is actually f of c for c in AB. Now we're actually going to use the mean value theorem for definite integrals that you learned in the last section. So what we're going to do is we're going to take c between a and b in the open set and consider x in a and b where x is greater than c. So the first case is going to be where x is greater than c, and the second case will be where x is less than c, just so we can get limits from each side to get the actual limit. Then what we're going to do, again, like I said, do the right limit, that is x approaches c from the right, of g of x minus g of c divided by x minus c, which is the definition of derivative. And now, of course, we take the definition of g and we replace this g of x with the integral definition and g of c with the integral definition. Now, to make this process work, what we're going to do is invert the limits here and, of course, take on another negative sign to make this positive. So we're going to get an integral from c to a f of t dt, and then this integral we just write second, the integral from a to x f of t dt. And now we're going to use additivity here. Additivity works for any order of the limits, but here's a nice way to remember it. We've got the a here as an upper limit and a lower limit here, so we're going to push these together to give us the integral from c to x of f of t dt. And now this is where we want to use the mean value theorem. So we know that there is some z between c and x such that this definite integral is now f of z times the length of the integral. So what's nice about that? Well, the problem absorbs. And then we have the limit as x approaches c from the right of f of z. And then again, this is where we have to use the squeeze theorem. If x is approaching c, then z is approaching c by the squeeze theorem. And so we just get f of c, and I've written squeeze here. Now, just to be complete, let's now consider the example where x is less than c. And if you like, let me go ahead and write that down. This will be the case where x is less than c, just so it's complete and you know what I'm doing. And then, of course, now we go ahead and write the limit as x approaches c from the left of the difference quotient. Now, we don't have to do the same argument over because we know the result will just be the integral from c to x f of t dt. But now we want to use the mean value theorem for definite integrals, and so it makes sense that the lower limit would be less than the upper limit. That's how we prove that result. So we flip them, and of course, that carries the negative sign by definition. Now we can actually invoke the mean value theorem. We have the z between x and c, so we get the negative f of z divided by c minus x, that is the length of the interval, But of course, the negative c minus x is x minus c, so the x minus c is absorbed. And now we're back to the same argument as before. The limit as x approaches c from the left of f of z will again be f of c in a similar context as what we have here. And so now we have the left and right limits existing, and their limits are the same. Therefore, the limit of the difference quotient is f of c, which is exactly what we decided that we needed to do. And we are done.